Welcome back to Statistics. So far, we've been discussing the mechanics of significance tests, the things like p-values and critical values and rejection regions. We've been discussing those ideas in the context of two-sided alternatives. So how does it work when the alternative is one-sided? We want to take a look at that in today's video. What we're going to find is that essentially all the concepts remain the same, but the definition of what counts as extreme essentially changes depending on the nature of the one sided alternative. So let's see how that works. So, when we're doing a one tailed test, the ideas of significance and p-values and so on remain the same, but the basic difference is that, as I said, what counts as extreme changes. Essentially, the idea is that data to count as extreme needs to be extreme in the direction specified by the alternative hypothesis. So let's see how that works in an example. Let's consider our SAT prep course example. You may recall the idea was that this company has a preparation course for the math portion of the SAT, and they want to find out if it works. Uh, so if it works, it ought to increase the average score that people make on the math portion of the SAT. So that sets up a significance test of the null hypothesis that the average score doesn't change, it remains at 500, versus the one sided alternative that the average score is greater than 500. That's what it would mean for the course to actually work. So, how do these hypotheses stand up in light of the sample data? You'll recall the sample data from that example was in a sample of 60 individuals who were given the company's SAT preparation course. The average SAT math score turned out to be 525 with a sample standard deviation of 102.5. So we're going to find that the everything hinges on the alternative hypothesis here that mu is greater than 500. We call that a right-tailed alternative. Note also that sigma here is unknown, which means we'll be using T procedures instead of Z procedures. I mean, you could try to look at Z procedures if you wanted, but what you would immediately find is that the value you need to compute the test statistic, the z-score for x bar, one of those values is unknown, namely sigma here. So since we don't know sigma, we have to estimate the z-score for x bar. We do that by using our sample standard deviation as an estimate for sigma, and that results in what is known as the t-score for x bar. So you can see that the standard deviation of x bar has been replaced by the standard error of x bar in the t-score. And in the formula on the right there, the sigma, which was unknown, has been replaced by an s, which is the sample standard deviation. And that's essentially the only difference. This turns the z-score into a t-score, as we've said. And I would just point out that this really has nothing to do with the fact that we're doing a right-tailed test here. It simply has to do with the fact that sigma is unknown. This can happen no matter what kind of alternative you have. We basically use the t-score as an estimate for the z-score when sigma is unknown, and we interpret it in the same way. That is, plugging in what we know now to the t-score, we find a t-score of 1.8893, and you read that as our estimate for the number of standard deviations that x bar lies above the mean, assuming that the null hypothesis that mu is equal to 500 is in fact true. So we estimate that that sample mean of 525 is about 1.8893 standard deviations above the mean of 500, assuming that that is in fact the true mean. So how extreme is our data? Well, here I'm drawing sort of the same picture as before. I'm drawing now in terms of the t-distribution, right? Since our sample size was 60, we have 59 degrees of freedom. And you can see our t-score of 1.8893 there. It does look a little bit out in the right tail there. So it looks like we're getting into extreme territory, but we need to quantify things in order to see that a little more clearly. So what does extreme mean for a right-tailed test? Well, extreme means extreme in the direction of the alternative hypothesis. To see what that means in this case, you need to think of the middle of the t-distribution here as representing the null hypothesis, essentially, the null value of mu equal 500 that would be true if the null hypothesis were true. One way to think about that is that if the t-score were 0, then your x bar value would have been 500. And that would be sort of the strongest possible indication that the null hypothesis might in fact be true, is if you got an x bar of 500. But the alternative specifies that the mean is actually bigger than 500. And so extreme in the direction of the alternative hypothesis would mean t-scores that are greater than the null value. And so that would correspond to t-scores that are bigger than 0. So the direction of the alternative for a right tail test is values of t that are larger, to the right, in other words. So these then are precisely, the shaded area is precisely the data that is at least as extreme as our observed t-score of 1.8893. And again, the p-value is the probability of all this data. So the p-value for a test is the probability of all data that's at least as extreme as the observed data in the direction of the alternative hypothesis. And this would be a calculation you would do with the t-distribution with 59 degrees of freedom. And if you do that, you find that the p-value, the probability of all t-scores that are at least 1.8893, is about 3.19%. So our p-value is 0.0319. What about critical values? You'll recall that critical values are indicative of the boundary of significance. It's where our t-score would go from being statistically insignificant, in other words, in the middle, whatever, 95%, if 5% is our significance value, to significant. So what would be the critical value t star at the alpha equal 5% significance level for a t-test of our hypotheses here and a sample size of 60? Well, if the alpha value is 5%, we're going to reject the null hypothesis if the area in the right tail is 5% or less. So I've illustrated that here with the shaded area, which is 5% in our t-distribution. And what we're looking for is the boundary of that shaded area. Again, you can use a t-distribution calculator to find this. It turns out that that boundary happens with a t-value of 1.6711. So t star equal 1.6711 is the critical value for a 5% significance test in this right-tailed scenario. You'll recall that our actually observed t-score was the t-score for x bar of 1.8893. And so we do see that our observed t-score is in the rejection region. And so that tells us that we're going to reject the null hypothesis at the 5% significance level. You can also see by looking at the area to the right of our observed t-score of 1.8893 that the p-value is going to be indeed less than 5%. You'll recall it was 3.19%. So if you want to look at it from the point of view of the p-value criterion, then p is indeed less than alpha. And so this is an independent way of seeing that, yes, indeed, we're going to reject the null hypothesis at the 5% significance level. So our decision and conclusion at this point would be to reject the null hypothesis that mu is 500 in favor of the alternative that mu is greater than 500 at the 5% significance level. In other words, our evidence is statistically significant at the 5% significance level that the true mean is indeed bigger than 500. You can see maybe, even though I haven't illustrated it here, what would happen in a left tail significance test. Then the pictures would simply reverse from left to right. The p-value would be the area of the left tail starting at our observed data. And the critical value would be the t-score that gives us a left tail that's equal to our significance level. So everything would just sort of essentially, reverse for a left tail. And so there you have it. The procedures for carrying out a test when the alternative is one-sided are pretty much true to their names, right? Instead of looking at both tails for your significance level, your critical value, and your p-values, you look at the appropriate right or left tail. A right tail if you're doing a right tail test, and a left tail if you're doing a left tail test. So I hope this makes it a little more clear. And if you have questions, as always, let me know. We will be back at you real soon with more information on significance tests. In the meantime, take care.